All right, here we go. So today we're gonna still keep talking about the Grand Central Dispatch. There's a few comments, actually a few add-ons on the previous lecture, and we're gonna start about the Swift concurrency, which is gonna be the async await syntax. Okay, so we might go over actor model next lecture. So let's take a look at a few concepts I want to add to the last lecture when we discussed about the global queue. Okay, so last lecture I showed you guys one function call. You can submit tasks to the global queue, which is called like perform concurrent. I forgot the exact name, but you can you guys still remember that, right? Can do concurrent task on the global queue. Okay, but like the more generic way to access the global queue is, well, simply access the global instance on the dispatch queue class. Okay, and of course you can specify the quality of service, like in any other queues. You can do like background or user initiated or user interactive or default one or even the utility one. Okay, and of course it's a normal queue. Well, it's a concurrent queue, just like other concurrent queue you have seen before. Okay, so you have async and sync. Okay, so you can choose whatever behavior you want. Okay. Now let's add one more point to the synchronization part. So first, take a look at this one. Okay, so this code block. So internally, all the collection in the Swift standard library is not thread safe. Okay, there's no locking mechanism behind the thing. So if you want to achieve a thread safe collection, you have to implement that on your own. Okay, so take a look at this one. So I call that as thread safe collection. Okay, and I use a generic type here. Okay, the label for the generic type is called element, which stands for the element we want to store in that collection. Okay, so we have a private elements, private local variable in this case. We haven't go over the access control in Swift. Maybe we won't have the time, but if you guys are already familiar with some other language, you probably already see this private keyword before, right? Okay, so if you don't understand that, just ignore that. So we have some local variable named as underscore elements, which is going to be the actual internal collection we want to manage. Okay, and we provide two things. First one is another computer variable. In this case, we're going to use this computer variable to actually let user to read from the internal data. Okay, you can see just simply return the underscore elements. Okay, and another function call is called append. So we want to append something to that collection. Okay, so again, we're going to simply just call the append on the underscore elements. Okay, so any problem here? We're seeing any problem? So it's not thread safe. Okay, so for example, what if we have multiple threads trying to concurrently access? Well, maybe some thread wants to read from data, some thread want to append to the data, and they are kind of interleave between each other. Okay, so it can cause data risk. Okay, so any solution to that? We have discussed that in the previous lecture, which is gonna use a serial dispatch queue. Okay, so let's see this in action. Okay, let's see this one. All right. Now this is also another code template in the gcd.playground. Okay, it's already on the website, on the official repository for our course. Okay, is that big enough for you guys? Maybe a little bit larger. Okay, so any idea how we're supposed to achieve that with a serial queue, which we already discussed before, right? Come on, you guys guide me to how to do that. Yeah.
We can use queues as sync.
Yeah. So so first of all, we want to create a serial queue, right? Okay, let's do that. Again, we're gonna do a private one, but anyway. Okay. put private here. We're gonna say let queue with dispatch queue. Okay. Wait, what's going on here? Just give me any. Should be label. Maybe say thread save here. You can get whatever name you want. Okay. Actually, let me take a look at the why the Well, it seems right, but I don't know why the Xcode don't give me any code completion here. But anyway, so you have a dispatch queue, and in this case, it's gonna be because we didn't specify the attributes. Okay, so by default, it's a serial queue. Okay, so we have the queue. How to use this one to protect our read and write. Okay, so what I mean by read essentially means when the caller want to access this one. Okay, what I mean by write essentially means some caller want to call the append to write something into the internal collection. Okay, so we can use the queue.think. Okay, so just like this. Okay, and of course we can also say queue.sync here. Okay, does that make sense? Now we have a thread safe, collection. Okay, but so first we want to try to improve a little bit upon this one. So first thing you need to notice is for the append function. Okay, right now we are using the sync. Okay, but the problem is, what if, just imagine, what if we already, there are thousands of threads trying to, maybe we have already thousands of threads to read from this collection, and also we want to append on this collection. There are already lots of threads trying to do that. Okay, now what if we want to append something? Okay, in some other threads. So that thread is going to be blocked because it's a sync method, and all the you have lots of tasks before that one. Okay, so you kind of blocked for a long time. Okay, so for the append action, you just want to say, okay, I want to append something to that collection, and that's it. I don't want read anything back. Just do some action which doesn't return anything. So in this case, I can try to improve that a little bit by replace this sync one with async. Okay. Does that make sense so far? So when the caller trying to call the append function, okay, you're just gonna submit the task and return. Okay, it won't block the current thread. Okay, so kind of a little bit improvement upon the original version. Okay, now there's still a big problem. So we are using the serial queue to achieve a thread safe collection. It is a thread safe, okay? But the problem is we also want to concurrency. Okay? Right now, even though it's a thread safe, but when we are trying to access this data or append this data to this internal to this collection, we don't have the benefits from the concurrency, because all the action is serialized. Okay, so any idea how we're supposed to improve on this one? Well, just simple one. Change the serial queue to a concurrent queue, right? Well, it's a start, but you're gonna see, other problems. Okay, so let's first try to change this to concurrent one. Let me try to indent this in a little bit. Okay, so now you can see we have a concurrent queue. Okay, now you can get the benefit from the concurrency because they dispatch things concurrently. Okay, but now the problem is, again, we can have data risk in this case. It's not thread safe anymore. Does that make sense? you can take a look at this. Well, just like let me see. Okay. Actually, let me try to go back to the Xcode. Sorry. No, sorry. The slides. Okay. Let's take a look at this scenario. Okay. So right now we have a concurrent dispatch queue. Okay. And for example, right now in that queue we have multiple actions. First one is going to be a read, and next is append, and followed by 2 read operation. Okay. So what if now we dispatch the read and append and the next read to 3 threads, because it's a concurrent queue. Okay, it can do things concurrently. But now you can see again. Now you can interleave between read, append. Okay, which again causes the data race problem. Is that clear? Why the data race can be a problem in this case? Okay. Now let's take a look at the kind of rewind of all the process we have done so far, and think about what kind of behavior we actually want to achieve. Okay. So first of all, we want to make it thread safe. Okay, it's our goal. Okay, in other words, there's no data race even with concurrent access. But however, well, you cannot make the append concurrent. Okay, so at the same time, we want to utilize the power of concurrency, which means we want to concurrent read. Okay, but serialized append. Okay, so a kind of combination between 2 different approach. Okay. So in short, we want to concurrent read, but serial write, in this case, going to be append, okay? And people often use the special lock to achieve this behavior, and they usually named as read-write lock, okay? Are you guys familiar with that one? So, in some language, they provide this lock in their standard library. For example, I believe Python have one, just named as RW lock, stands for read-write lock. Okay, so by using this lock, you can achieve a behavior where you have a concurrent read but serial write. But again, you're going to use a lock. But in this case, we are going to try to use the dispatch queue and achieve a lock-free read-write lock kind of behavior. Okay, now let's take a look at this new concept. It's called dispatch barrier. Okay. Now, the orange block stands for a task with barrier flag. Well, in this case, it means we want to make this task as some sort of barrier. Okay, we're gonna explore the barrier later. So right now you can see we have all 3 read operation here. Okay, they're just like normal tasks. Okay, but we have the append operation. But in this case, append is gonna act like a barrier. So, and you can see all the write operations are marked as barriers. Okay, so let's take a look at the behavior of a barrier. So, what does that mean to be a barrier in this case? So, a barrier follows 3 rules. Okay, so first rule is when you're trying to add a barrier to a concurrent dispatch queue. Okay. The queue delays the execution of the barrier block and any task submitted before the barrier until all previous submitted tasks finish executing. Okay? So in short, it means when the dispatch queue saw a barrier in the queue, okay, it's just going to wait and trying to finish all the tasks before. Okay? And when it reaches to so now let's go to the second rule. When it actually reaches to the barrier task, okay, you're gonna execute the barrier task one by one. Okay. Now, the last rule is when you actually finish all this barrier block, okay, the queue just resume to its normal behavior. Okay, so like if it's a concurrent queue now, when the barrier block is finished, now you can schedule things concurrently again. Okay, is that clear? All these 3 rules so far. Okay, that's from the Apple's official documentation to describe the behavior of a barrier. Okay. Now let's take a look at how the barrier, so how all these three rules apply to this scenario. Okay, so again, we have the same situation before. Now, first, we're gonna just let you guys make a guess. So what kind of behavior we're gonna have right now? So what if we want to schedule things from the concurrent dispatch queue right now? So, yep.
Everything up until the orange will be scheduled, and then once they're done, then the orange will go in by itself. Once the orange is done, then everything else will be scheduled.
Yes, exactly. So in this case, first thing we're gonna schedule is the read. But since the append, the second task is a barrier, so we're gonna leave that alone, but just schedule one task, which is gonna be the read, okay? So even though it's concurrent dispatch queue, but it kind of hits a barrier, okay? So it only execute the read, okay? Now when the read actually finished, it goes away, right? Now we can execute the barrier block, okay? In this case, following by the second rule, the barrier block, again, should be executed serially, okay? Now, so maybe in this case, the dispatch queue kind of schedule the barrier to the second thread, okay? Maybe it can go back to the thread 1, okay? It's not defined, okay? It depends on the internal implementation of the Grand Central Dispatch, okay? Now, when the append were actually finished, now this queue can return to the normal behavior. It's a concurrent queue, okay? So you can schedule both read operation concurrently. Okay, is that clear so far? Now, let's take a look at another example in this case. Okay, now we have two read operation followed by two append operation, and these two append operation again gonna be marked as barrier. Okay, and followed by two read operation. Again, assume right now for the dispatch queue we have 3 threads available, okay, to schedule things. So first thing is, well, it's a concurrent queue. So it's gonna, well, trying to dispatch 2 read operation concurrently. Okay, so now you can dispatch 2 read operation to this thread 1 and thread 2. Okay, but now it also hits the barrier. So you're only gonna schedule these 2 instead of 3. Okay, now when these 2 finished, when these two tasks finished, now the concurrent dispatch queue can actually execute the barrier block. But again, the barrier block gonna be executed one by one. Okay, so first you're gonna dispatch the first append operation, and then when it's finished, you can schedule the second one. Okay, and when all this barrier block finished, okay, now it resumes to the normal behavior, which is gonna schedule things concurrently. Okay, is that clear so far? Okay, so after knowing these concepts, we can take a look at how the syntax looks like when we're actually trying to use this barrier feature. Okay, so you can see right now here, when we trying to execute some tasks with the barrier flag, okay, we can put a flags into, so the async call can take a flags argument, okay? In this case, you can go with .barrier. There are actually, well, some other flags in this flags. You can take a look at the documentation and explore all different behavior with other flags, okay? But today we're just gonna talk about the barrier. So this is how you actually to create a barrier block, okay? Now let's try to use this concept, use this barrier to achieve lock-free concurrent read, but with serial write, okay? Now let's go back to our ASP code. Let's take a look at this thing. Okay, now we have concurrent queue, right? But again, this one is not thread safe. So any idea how we use the barrier to solve this problem? Any idea? Yep.
On line 93, we add the flags with barrier.
Yes, exactly. So we can put a flags here, okay? and this flag gonna be barrier. Okay. Now we have a thread safe collection, but at the same time it supports concurrent read. Okay. So when it comes to the append operation, which is gonna be a write operation, okay, it behaves like serial operation. But when it comes to the read, you can execute concurrently. Is that clear how we achieve this behavior? Okay. If you're interested, you can go online to check the read-write lock. Okay. You basically have the same behavior as like what we have done right now. Okay. Okay. Now let's go back to this one. Now, some notes regarding the dispatch barrier. So first, well, it's pointless to use a barrier on a serial queue, okay? Because, well, it's a serial queue. No matter what you've done, you only execute things serially, okay? So barrier has no, effect on the serial queue. And the second one is, it's really dangerous to use the barrier on global queue. So whenever you want to submit a task to the global queue, do not use barrier, okay? Well, at least right now, I cannot think of any use case you want to use a barrier on global queue, because it's really dangerous. You don't want, because the global queue is kind of shared by the entire system. You don't want to block that, okay? Other apps, other system resources might kind of use that queue to do some critical tasks, okay? So don't do that. Now let's take a look at some other codes in the by using the Grand Central Dispatch, okay? So we have seen the async await version of using the URL session before, right? Now you can take a look at how we, in the old world, like a few years ago, how we can achieve this thing by using Grand Central Dispatch. So the URL session also have the shared instance also have something called data task, okay? And internally, that data task actually gonna kind of using this Grand Central using the dispatch queue, okay, to dispatch the task to some background thread, okay? And this thing, okay, you can see this trailing closure, okay, at the end of this data task. Usually we call that as completion handler, okay? So actually I have done something similar before in the lecture when we're trying to create actually, let me show you. So let's go back to our project, okay? So let me see, where did I find this one? View model. Yes, take a look at this one. So we have defined something called load image, okay? And it takes a argument, in this case, gonna be a closure, okay? We're gonna execute this closure when we actually fetch something back from the remote server. And this one, usually we can call that as completion handle. It means what kind of behavior or what kind of code we want to execute when the entire process is finished, okay? Is that clear, like the concept of completion handler? All right, it's just some fancy name for certain type of closure, okay? Now, let's go back to the keynote. Okay, so is that clear? So this function block so when you submit the data task, you're gonna, like in the background, you're gonna trying to communicate with the remote server and trying to fetch some data back, okay? And when the process is done, you're gonna actually execute this closure, okay? You pass it in. In this case, you're gonna check the arrow, right? In this, you can see here, you can check the arrow, okay? You can also grab the data. In this, data gonna be optional, okay? So you have to first check the data. And in the end, you can use the data. For example, you may use the data to, well, update some UI, okay? And of course, you can see, in this case, we have to make sure all the UI updates happens in the main thread, which I already mentioned before, right? And by using the Grand Central Dispatch, you can use the dispatch queue.main, to push all the tasks to the main threads. Okay, is that clear? Okay, now let's move to the Swift concurrency. Okay, the Swift concurrency majorly consists of three concepts. First one is the async await keywords. Okay, the second one is called task system. Okay, and the last one is called actor model. Okay, we're gonna go by all these three things one by one. Okay, but first let's ask a big question, like why? Why we want Swift concurrency? Because we already have the Grand Central Dispatch, right? We have dispatch queue. We can do concurrent. We can achieve concurrency with like a great tool. Okay, but the thing is, the Grand Central Dispatch also have some problems. So let's actually take a look at the Swift evolution proposal, which is labeled as 0296. Okay, this is a proposal where people initially discussed the proposal of supporting structured concurrency by using the async and await keyword. Okay, any of you know about this Swift evolution thing? Yeah. Okay, so basically it's kind of GitHub repository. Okay, where people can submit their proposal. Okay, let's take a look at this thing. Here we go. So this is the original proposal for making for supporting the async await. Okay, and they made some really nice example to explain why we want this behavior, why we want this feature instead of using the old Grand Central Dispatch. Okay. Now, first problem here is something called pyramid of doom. So, in the previous slides, you have seen how we can use the completion handler, okay, to execute something when the async task is done, okay? But the problem is, what if you have like multiple, function call? They are all async, okay? In this case, like for example, like let's assume they all support like completion handler, but like doing that, you can have a lot of nested function call, okay? And all this nested function actually is some, completion handler. For example, in this case, we can call something like load web resource, okay? And it takes, it's async first, and it also takes a completion handler, okay? And inside this completion handler, when we actually retrieve something back, okay, we can also, again, call say load web resource. In this case, we're gonna load some other data. And again, it's an async function and takes some other, takes another completion handler, okay? And you can see all these things got nested, inside each other. And it's really ugly and it's really hard for you to actually to reason about how the code flow actually, works, okay? Well, I mean, in this case, it's really simple example. But when you do lots of other stuff, it can get really, really complicated, okay? So, as you can see here, we mentioned, makes it difficult to read and keep track of where the code is running, okay? Now, another problem is the error handling can be really a big problem, the pain in the ass, when you're trying to use all these completion handlers, okay? So let's take a look at this first example where people use the guard let to check the error, okay? You can see again, this is the, kind of similar scenario than the previous example, okay? But in this case, let's assume the data resource here is gonna be the optional. So you have to do lots of, error checking, like optional unwrapping here, okay? And you can see the entire code, looks really ugly in this case, okay? And the structure is really complicated and sometimes it's really hard to follow, okay? Does that make sense? It can be a problem, okay? Now let's skip this too. I haven't go over the result, but let's skip this too. Just some different style when you do the error checking, okay? Now, we're also gonna skip the problem 3, but if you are interested, you can go over this proposal later, okay, and to take a look at all the cases they mentioned, okay. Let's take a look at this problem 4, okay. So they say many mistakes are easy to make. So why is that? For example, in this case, we are using the guard leg to do the error checking, right? But, I mean, if it's in the else branch, it means this data resource is is the option is a nil. Okay, it means something goes wrong. Okay, nothing goes back. Okay, in this case, well, of course we're gonna return. Right, we just stop right here. But the thing is, when you apply a completion handler, usually you want to do some error handling or special things when this entire thing complete. Okay, so you should call the complete handler before this return. Okay, but you can forget this one easily because, well, there are lots of error checking happening and you can see all this nested within each other and it's really hard to follow. You can forget that easily, okay? And when you forget this thing, actually it's really, really hard to debug. You just cannot remember, you kind of missed one line of code somewhere, okay? And you didn't see, when sometimes you see nothing is happening, you may wonder, where's the bug? But it's just missing one line of code here, okay? Now, so this is like majorly, several problems. Why? And these problems make people thinking like we might want a better version, a better support for the concurrency, all right? So people made this proposed solution with async and await. Again, we can see this is kind of similar example here. We have to, process the data somehow, right? And in this case, we have the async await, and we can, design these 3 functions as an async function. Okay, and when you actually program this function, you can see all these things just like some natural, programming in a single-threaded scenario, right? Just one by one. You can see the structure clearly. Okay, there's no more confusion when you nest the things, like all the completion handler, all these closures within each other. Okay, is that clear why we want the async await? Okay, so when people start talking about the async await in the Swift, the major goal is not the performance, because actually the Grand Central Dispatch has a great performance. Okay? The major problem they want to overcome is the readability of your code. That's the reason why this async await, the Swift concurrency exists. Okay? Now, let's talk a little bit about the concept of structured concurrency. Okay, so how many guys have heard of this one before? Okay, so again, it's just some fancy terminology. And when people say something like as structured, it means you can do something in a natural language flow. Okay? So for example, in this case, the concurrency can be achieved in a natural code flow, and we call that a structured way. Okay? And actually, we have been programming in a structured way for a long time. Okay? Because we have the if-else statement, right? We have the switch statement, okay? We can call the function call, which internally gonna jump to some line of instruction on the CPU, okay? And with all this power, we call this as structured programming, okay? In comparison, non-structured programming may use this go-to statement. Are you guys familiar with the go-to statement? To kind of jump to somewhere in the code, okay? And this is non-structured programming style, okay? Now, it's kind of like similar to the Grand Central, like the usage of Grand Central Dispatch. We pass lots of completion handler, right? And the completion handler can be executed sometime in the future, okay? It's really hard to trace. Okay, so as I mentioned, like however, using the Grand Central Dispatch for the concurrency is still a non-structured way of programming. Okay, despite the entire language actually supports a structured style for a single thread scenario. Okay. Now again, well, that's some code example from the previous WWDC, and you can see, well, this is an example of using the Grand Central Dispatch, and it's really ugly actually. Lots of things, nested with each other. Okay, and you can have a simplified version of that. Okay, again, this is the example from WWDC, and this is a simplified version of the this function called fetch thumbnails. So the text is maybe a little bit small because it's a screenshot, but you can go over these slides later. Okay. Now let's talk about the async await. Okay, the async await, they're just two keywords. Okay, they provide a structured programming style for the concurrency, but it does not come with the support of concurrency. Okay, majorly it just provides the structured way of programming, but it does not support concurrency. Okay, it's kind of two concepts. But anyway, when you're trying to do things like more applied, you don't need to worry about these things. So the async await is integrated as a language feature of Swift. Okay, so that's why people call that as Swift concurrency. It's right integrated into the compiler. Okay, when you want to achieve the async await, you usually need the native compiler to support this feature, because the compiler needs to translate the corresponding function call into some sort of state machines. But anyway, if you don't understand this concept, it's okay. So it's kind of related to the internal implementation of the async await. Okay? So just wonder, like, how many guys have ever tried to look into how the async await actually works behind the scene? So it's kind of the huge state machine. That's really, really interesting thing. I haven't actually take a look at actually you cannot take a look at the Swift because it's not really open source. But the implementation of async await in Rust is really fascinating. Okay, basically a state machine. But anyway, if you're interested, we can discuss this one after this class. So let's go back to the Swift concurrency. And now let's go to the next topic is task. Okay, as I mentioned before, this async await, there are just two keywords. Okay, they does not come with the concurrency support. Okay, so we have to use something called task. Okay, in this case, take a look at this example. You have seen this before, which this is kind of sort of the view where we make the editorial feed view to display all the images. Okay. Now take a look at this case. When we want to call the await function, okay, well, in this case it's gonna be a load editorial images. It's an async function. It's awaitable. Okay, so we're gonna await on that function. But this case we use this one in this function called onAppear. Okay, do you think this is actually gonna work or not? Okay, so the compiler, well, of course, gonna give you some error. It says invalid conversion from the async function to some sort of synchronized function type. So the reason is, by default, all the code we have seen so far, they are living in the synchronized context. Okay, so when you want to start some tasks, in a concurrent context, you have to be explicit. Okay, in this case, we can use this concept of task. So now let's take a look at this new thing. We can create, like manually, explicitly create the concurrent context by using this thing called task. Okay, it takes a closure, and inside this closure, it supports the full concurrency context. Okay, so this one is actually equivalent to when you're using the .task. They are equivalent. Okay. Now, of course, you can set priority for the tasks. Okay, so the task can take a parameter named as priority. Okay, you can take a look at the documentation of this class, and there are some different options here. So for example, in this case, we're gonna use the user initiated. Okay. Now, let's take a look at some features, language features. First one is called async let. Okay, so let's take a look at this thing. So Zoom, we have some function called named as calculation, and this is an async function. We can await on that, and we're gonna await this data to be later assigned to this result variable. Is that clear? Now, well, of course, you're kind of living in some function call, right? In some definition of function. So you have some preceding statements. Of course, you have some following statements, okay? Now, let's take a look at the code flow in this case. First, you're gonna execute all the preceding statements, right? And when it reaches to this calculation, because you're gonna await on that function call, okay? So you kind of wait the calculation to finish. In this case, the task system gonna suspend the execution of your function. It's gonna suspend that and to do something else, okay? Until your calculation function actually return the value. Now, you're gonna assign the value to result and resume this function, okay? And when it has a valid result, you're gonna actually execute all the following statements. Okay, is that clear? Now, there is some problem, well, like there are some improvements we can have, because right now, from the caller level, we can see this thing still kind of support the concurrency. But in the internal level of this function call, this thing, well, kind of execute all different functions serially. Because when you reach this one, you have to wait, okay? But you may want to sometimes to do some another, additional heavier task after this result, but you're gonna use the result maybe later, okay? So you don't want to wait so long. So now let's take a look at this function, the feature called async let. Let's change this syntax to this one. So now we have, say, async let results. Assign symbol with the calculation, but there's no await keyword before the calculation, okay? Now, of course, we have preceding statement and following statements. Now let's take a look at the code flow. Again, we're gonna first start with the preceding, execute all the preceding statements, okay? Now, when it goes to the calculation with async let, you can actually create a child task and run things concurrently, okay? So we'll not block the current execution. So the code actually can, well, in this case, the calculation just gonna assign a placeholder value. It's not really a valid value, just some placeholder, okay, to the result. Now, this thing is still gonna, all this code gonna still execute, okay, without any interruption. And you're gonna execute all this following statement until you reach some point where you actually want to use this result, okay? And you say await result, okay? And when you say await result, of course, you're gonna await the calculation to finish and actually assign the final concrete value to this one to replace the previous, the placeholder one, okay? Of course, you can do other things concurrently in this block, like saying following statements, okay? Actually, we are running out of time, so we can stop right here. Actually, if you guys are interested to take a look, kind of quick look at this example. Let me see. Actually, I created an Intel new project here because the playground seems to have some bug with the student concurrency right now. So I created an Intel project. But you can see, first I have a function named as run task. Okay, I basically call the fetch result function and print something out, print the result out. Okay, and the fetch result have two calculations. Okay, the first calculation just gonna sleep maybe 2 seconds, and the second one just gonna sleep, well, again 2 seconds. Okay, and they're gonna print the start and the finish. Okay, and the first calculation gonna return 1, second calculation gonna return 2. Okay, and inside this fetch result, I'm gonna add this result up and add 3 after that. So, well, the result should be 6. Okay, 1 plus 2 plus 3 should be 6. Okay, And you can take a look at the example here. We just use the await in both statement. Okay, let's actually trying to run this thing and take a look at the console here. Here we go. You can say it started with task 1, but I have to wait. Okay, you have to wait to finish the task 1, and then you can start the task 2. Okay, and you can see it takes 4 seconds to finish the entire task. Okay, actually we can cut it down to 2 seconds with async let, but we're gonna go over this in next lecture. That's all for today. Sorry for the late.